seeing my content. So today we'll start with whole numbers, yeah?
Yeah.
We're doing number theory for grade 9, and we'll start with whole numbers. Okay, read for us the first chapter so that we take notes.
The set of natural numbers is a subset of whole numbers, which is a subset of integers.
Okay.
The set of integers is a subset of rational numbers, and all these numbers form part of the real number system. This can be represented like a family tree of numbers.
Okay, that's great. So they started with natural numbers. Why do you think they're called natural numbers? I just want to hear your thoughts on that. I'm not expecting a correct answer. I just want to hear your thoughts on that. You don't know? Okay. They're called natural numbers because you can count from 1, 2, 3, 4, 5, all the way up to 9. So those numbers you can easily count on your fingers, right? So you've got 10 digits, 10 fingers. So there's one hand. And there's the other hand, right? All right, so because you can count from 1 to 9, those are called natural numbers, right? And then you get whole numbers where when we add the number 0 to the number line, to the number system, right? We are making it so that we can be able to jump after 9. What do we have? After that number that we have after 9, what else can we have? And what happens every time we count after the 9? So from 0, which is part of the whole numbers. So let's start here. So natural numbers would be 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? And then whole numbers would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? And these ones, they give us an indication that after the number 9, we can have a number like 10, right? And that helps us now count as we would with our fingers, but also having the number 0, because we can represent 10 as 10 times the first number, then we can have numbers like 11, 12, 13, all the way up to 19, and jump over to the next count, which now goes from 20, and do again at every 10, we do 30, 40, 50, etc. So the number 0 helps us with that, right? Then we have integers. Integers, you and I, we've struggled quite a lot with that. Okay? -1 plus 5, those additions. That's where integers become important. So they're symbolized by this Z with 2 numbers like that. And it's literally on the number line, if you have 0 there, and you have negative in that direction. So I'll just close this since we're not in a call per se. That one. And then we've got rational numbers. I forgot what the symbol is for that, but let's just look it up. Rational number symbol. Rational number. The symbol looks like, yes. Rational numbers are symbolized with a Q that has a thing like that. Right? This is rational numbers. And rational numbers simply tell us it can be expressed as the quotient or fraction of two integers, a numerator and a non-zero denominator. So remember what we spoke about the other time about a sum being the answer you get when you add two numbers. Remember we spoke about that in one of our classes. And then a difference is the answer you get when you subtract two numbers. One is subtracted from another number, right? That's difference. Product, remember when we were doing factorization, product was something times something is the answer. That answer is called a product, ne? So that's product. And then quotient, which is y, I guess the symbol looks like a Q like that, ne? Is the answer you get when you divide two numbers. Now it's important that you notice, so I want this sign here divide. It's got a dot and a line in the middle. That shows you it's a fraction. That already the symbol tells you it's a fraction. That's what it communicates to you visually. We have eyes to see, so if you can see that, then you must know when you see that sign, you see some number over a number that is not zero. Now, a rational number then becomes, an example would be a half, would be a quarter, would be 7/8, etc. Right? Now, it's important to note that a quotient, or rather a rational number, is a number that can be expressed as a quotient or a fraction of two integers. Integers being, those numbers can be negative or positive, right? And the one at the bottom, the denominator, must not equal 0, all right? So I'll just put there, rational numbers okay, so it's like a fraction and has a numerator and a denominator. Denominator that is not equal to 0. Because if it equals 0, then we get an undefined answer. All right? Yeah. And then the next one. So all of these numbers form part of the real number system. And now there are many different uses for both the real number system and the imaginary or non-real number system, right? What I learned from engineering students who were doing other types of engineering than the one that I was studying was that the non-real or imaginary number system is used when designing or implementing systems that have to do with transmitting a signal into space, right? So how we get DSTV is based on the imaginary number system. So it's an example of where math is applied in real life situations. Of course, if you want to study the math, it might be boring for a lot of people, but that's just how it works. So if there's a satellite to make sure that you get internet in the home or TV in the home, just know how that works is based on the imaginary number system. But in the real number system, which is how we work, which is where we usually work right up to matric, I think that's where we should pay attention. So let me just skip. Okay, so I like this schematic, because it shows you complex numbers, which I guess maybe all numbers could be complex if we thought about it like that. But when we break it down, like they say here, represented like a tree or family tree of numbers. You know, almost family tree, it's you there, then it's your mom, then it's your dad, then it's her mom and her dad, his mom, his dad, etc. So that's an example of a tree, right? A family tree. Even the ones we were doing in probability last week, right? What do you call them? The name escapes me, but you remember them for probability. Yeah. So here, in the complex number system, we have real numbers. And these are indicated like that, right? Then we have imaginary numbers. And imaginary numbers, it's that R with a, it's a R with a thing there on top, ne? All right. Now in the real number system, we've got rational, rational numbers, so like your halves, -3/4, etc. Ne? And then we've also got irrational numbers. Irrational numbers include numbers like pi, or there's a number of them. So irrational numbers, okay, it's Q with a thing, and it has a prime there. Okay, so these ones, rational numbers, we'll just make examples here. There's like 1/2, -3/4, etc. Ne? Irrational numbers would be pi, square root of 2. You see, so square root of 2, when you punch it in on your calculator, so let me just show you an example on the computer's calculator. Right, if we take square root of 2, that gives us 1.41421 something something, and this number can go on for an eternity, because there's a way that it's being devised that all calculators use, that if you apply the same way to calculate this number, you go on and on and on and on and on until, God knows when. Yeah. So numbers like this, numbers like pi is this that you use when you're working out area of a circle or perimeter of a circle. Anything that has to do with circular shapes, a lot of times you have to apply the use of pi to calculate stuff like that, right? Can be half a pipe if you're looking at the flow of water through the pipe, etc. Or designing a size of a skateboard half pipe if you want to take it that far, right? 3.14 what. That number can go on and on and on and on and on forever, right? So such numbers, they're called irrational because it's not easy to rationalize them as a fraction, which is an answer to something divided by something. So if you can say this divided by that, even if it's a fraction, the fact that you can say it's a number that's 1 divided by 2 and it's half, the fact that you can identify it like that makes it rational, even if it's a fraction, even if you can put it as this. Do you have a question? Okay, cool. Then the next one. Right, so in irrational, we've got surds. And surds are these ones, both square root of 3, square root of 2, etc. Right? And then these ones are non-terminating, non-recurring decimals. So non-terminating, non-recurring is both pi and Euler's number or something like that, right? So non-terminating. Terminate means to end, right?
Yes.
Oh, so you've watched Terminator before?
Many times.
Alright, cool. That's very good, right? And then within the rational number system, we've got, again, a branch called integers, which we've spoken about several times in our classes as well. And we've got fractions that are terminating and recurring, right? That terminate, and recur. So recurrence key, like let's say you've got the number, a fraction, a rational number, right? Let's say we've got a rational number and it's 1 divided by 3, right? So it's 1 over 3. So it gives us 0.33333333333, right? So this, you keep doing the division of 3 into 1 and you'll do it step by step by step by step. You'll keep having the 3's all the way to eternity, right? A similar example is 2 divided by 3. And so the calculator rounds off the last one as 7 because it cuts it. It's forced to cut it there. But the rules of rounding numbers up or down are that if you cut where the number that you cut at is 5 or more, then you round up. And if it's 4 or less, then you don't round up, you just keep it as it is. So the 0.33, for example, because it's 4 or less, we don't say 0.34. You just leave it as 0.33, so you don't round up or down. But because this one, it's 5 or more, so 6 is more than 5. So you round, so at the last 6 where you cut, then you look at the number after. So let's say we've got 0.666 and we decide to cut here, right? So then we say, okay, when we round, we'll say this is 0.667 because the number here is above 5. So it makes this one plus 1.
Oh, yeah.
That's how we round up or down. But in the case of 0.33333, if we cut here, because this is 4 or less, then we keep it as it is. Yeah, that's how we round up and down. So just remember that for future. So yeah, anyway, back to recurring. So those are examples of rational numbers that are recurring. But there are ones that terminate and don't recur, like half, like a quarter, like 0.25. You see, there are rational numbers, they are fractions, but they don't recur and they terminate. So you can do the operation of dividing the numerator by the denominator, but you'll stop somewhere. Yeah, one. So those are fractions that terminate. And then lastly, for integers, we've got whole numbers. And that's n with a subscript 0. So that's 0, 1, 2. And then we've also got natural numbers. Natural for obvious reasons. We can't, if we're counting the number of objects on the desk, it's 1, 2, 3, 4, 5, 6, 7. We can't count 0 objects. So naturally, we can't count 0 objects. That's why they're called natural numbers. But now in order for us to be able to add stuff up, at some point, some ancestor was like, okay, I've got 9 cows. How do I account for the 10th one? Then the number 10 is developed. Okay, now Mhlapo Waka is double the size, so I've got 20 cows. How do I account for, you see? So having numbers like 0 take us then from the natural number system to the whole number system. So when they are whole, then we're able to take stock and count and stuff. Yeah. So that's the long and short of this, right? So just read the next part.
You can see that the real numbers system consists of all rational and irrational numbers.
Okay.
Rational numbers can be integers, fractions, or recurring decimals. The integers include all negative numbers, positive numbers, and 0.
All right. So Wawana is just describing our drawing there. Carry on.
All the positive numbers 1 to 34 are called the set of natural numbers.
Okay.
If we add 0 to the natural numbers, we
Mm-hmm.
get the set of whole numbers.
Excellent. Okay, carry on.
Numbers that are not real are called imaginary or unreal numbers. For
Mm-hmm.
example, square root of -2
Okay, and there's
has
a
no real solution, and these numbers are not studied at school level.
yes, that's true. Yes, that's very true. We only learned about the imaginary number system in engineering class. So for maths, yeah, when you do that, yeah. So, okay, I just want us to read this part here as well, ne? Because I think it'll explain a lot, and it also revises stuff from grade 8.
In grade 8, you studied whole numbers and integers.
Uh-huh.
All the other numbers on a number line that make up all the real numbers are either rational or irrational.
Okay.
Here is a number line showing a few rational numbers and irrational number.
Okay, so let's make an exercise here between the two of us. So we're gonna start a number line here. We're gonna have a number line here, and we're going to plot it, ne? But I want us to plot it by starting first with let's start with natural numbers. So we'll do from 1 to 10, or rather, since it's integers and integers includes negative numbers and positive numbers, we'll say, okay, let's start with the integers. So let's do from 0 to 10, and from -1 to -10. Yeah. So we'll try and space those out. So let's say integers will color in blue. We'll use the color blue. But the point for 0, we'll leave it at that. So then we're going to also plot fractions, terminating and recurring, and we'll also do surds and other irrational numbers on the same number line, so that we can see how we can visualize the same numbers on the number line. And I'm doing this with the anticipation that it will help us, or at least rather help you, think about other things. Let's say you come across a problem and it's got the number pi. So you know if you multiply something that's around 3 with another number, what more or less you should expect. That's also another great tool to have in your arsenal when you're doing a lot of math problems. So I'm just saying that so that you can learn a couple of other tricks. Ne? So we'll start there, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Maybe we can slot in 11 there. So then on this side we'll have -1, -2, -3, 4, -5, -6, -7, -8, -9, and -10. Yeah. So these are our integers. Okay. Then, so for fractions, we'll use, yeah, so for irrational numbers, or rather for rational numbers, we'll use green. Yeah. So if we were to plot half, for an example, where would we put it? If we were to plot half anywhere on the number line here, where would we put it? Half, 1/2.
Half like
Yeah, the number, yeah. Like if we were to plot 1/2 somewhere on our graph, where do you think we would put it?
at 1.
At 1.
Yeah.
So you're saying half equals 1. That's what you're saying?
Yeah.
That's not correct. So if we have a 1 whole, and we cut it in half, is it still the same whole? They're not equal, are they? Okay. And if we have that same half and we cut it in half, do we still have a half? If we have that same half and we cut it in half, do we still a half? We don't have. Okay, so half is not equal to 1. Okay, so is it larger than or smaller than 1?
Large.
Okay, let's have one whole there. If I cut the whole in half, is that larger than 1?
No.
Is it smaller than 1? Are they equal? How? Because there's 1, now it's half. Is it still the same size?
Oh.
So half is not equal to 1 and it's not larger than 1. Okay, if we take that same half and we half it, is it still the same size as the half it was before? It's less than. If we do that exercise again,
Yes.
it reduces. Okay, so what does that tell us about fractions? They tend to be smaller than wholes, right? If you have, I've got 10 chairs here in this room, right? I took out 4, put them around the table. How many are left there? So if the whole is 10 chairs, if
6.
yeah, so that means in use, chairs that are being used is 4 out of 10. Chairs that are not being used is 6 out of 10. You see how rationing works?
Yeah.
All right, so this would be 2 goes twice, goes 5 times, 2 goes 3 times, goes 5 times. So this is also how we put fractions. So no, the number a half cannot be larger than 1. Instead, because it's exactly in the middle between 0 and 1, it would plot somewhere there. And then you'd have 1 over 2 there. So this is what this exercise in the book is showing you. How to think about numbers in terms of their relative size relative to numbers we know and can easily grasp. Okay, so we'll do a second example. Let's look at the same example. We're using 4 chairs and we're left with 10. Again, 4 chairs, but this is out of the 10 that are available. Yeah. So when we simplify this, we will say factorization again. So 2 is a factor of 10 and it is a factor of 2. And it's the highest that you can get, because if you multiply 5 by 2, you get 10. And if you multiply 2 by 2, you get 4. But if I use the number 4 as the highest common factor, it does not necessarily go inside of 10 and not leave any other number. And I cannot use 10 because it cannot divide into 4. So what do? I use the number 2 and I'll say how many times does 2 go into 4? It goes twice. And how many times does it go into 10? It goes 5 times. And then I'm left with that 2 divided by itself is 1. So then I'm just left with 2 over 5, right? So what does this tell me? If I take a calculator and I take the number 2 and I divide it by 5, then I get 0.4, all right? A half equals 0.5, okay? If we do that, so 1 divided by 2 is 0.5. So if I was to divide the numbers, the space between 0 and 1, let's say there's 0 and there's 1, and I divide it into 10 equal parts. So I'll have 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then 1.0. So here I would have a half, and here I would have 2/5. See, that's what we are learning here on this number line. But now we're including all real number systems. And I said rational numbers, we'll use green to identify them, and we'll use blue to identify integers. I see. So I think we'll also do the same exercise to include irrational numbers, just so you can get the idea. And then maybe we'll just read a little bit on that theory, just so you can at least make sense of, how it goes forward, how the theory goes forward. Okay. But so far, are we still together?
Yeah.
You're not just saying yeah so that I can finish talking and then 6 can chime and then you leave. I'm gonna remind you this video one day, watch. You see why I record my classes. So yeah. But anyway, do you see how? So I want you to just be able to realize how we can visualize these numbers on the number line, rational and some irrational. So somewhere there is 2/5, right? Another example, let's work out -3/4, right? -3/4. Firstly, what does this tell us about the rational number itself? What does this negative sign tell us about the rational number itself? What do you think it tells us? Any idea you have? Even if you don't know, it's fine. You don't know. Okay, it's fine. It tells us that it's on the negative side of the number line. That's what this tells us, right? So if we're going to plot it on this line here, then we would have to do that of division, etc. So let's say we use our calculator for now, right? So 3 divided by 4, 0.75. Okay, remember our little number line here. We can also do it going into the negative direction, right? And if we are at 0.5 in the middle, 0.6 should be just after, then 0.7 should be a little after that. So that means 0.75 should be between, so let's make it like that, all right? So that would be -0.5. All right, so if we have -0.7 there, then 3/4 should be somewhere there. So that means we'll have -3/4 there, which is -0.75. Are we still together?
Yes.
All right, -3/4. What happens if we have -7/3? When we do this calculation, we'll say how many times does 3 go into 7? 3, 6, it goes twice, and then it leaves 1 out of 3, right? And that gives us -2.3333. So let's just check. -7 divided by 3. All right, so it's -2.3 recurring. -2.3 should be somewhere there, so we'll say -7/3. Okay, so whilst this is a rational number, it is also an integer, or rather it's also made up of integers. Let me put it like that. It's a rational number made up of integers. So it could be the -7 that's negative, or it could be the 3 that's negative. But either or, the entire rational number is negative because one of the numbers, the numerator or denominator, is an integer. So it could be negative. Right, so I think that sums up integers. Now I want to put surds and non-terminating, non-recurring decimals, right? So let's take the number, let's take the rational number 10 divided by 4. Or rather, let's divide it by 3. I want to show you something. Let's divide it by 3. So it will equal 3 and 1 over 3, right? So 10 divided by 3 would be somewhere, let's see, 0 0.1, 0 0.2, 0 0.3. So the 0.3 would be somewhere there. And then I want us to compare it with pi, the number pi, right? You see pi is already showing up there. And that's because you're going to use it to work out the circumference of a circle. But I want to bring this exercise closer to that example there, right? So pi, it's 3.141, and then it has non-terminating, non-recurring numbers there, right? So this one would be, so 10 over 3 would be, 369, so this would be 3.3 recurring like that. So I just want you to see that if we have, let's say, the number 10 divided by 3 gives us 3.333 recurring, right? Okay, that's a fraction with a recurring decimal, right? And I want us to plot it somewhere there. So 0.1, 0.2, 0.3. So let's plot it somewhere there. So this would be 10 divided by 3. And I want us to see, you see, pi is a little bit smaller than 10 divided by 3 by about 0.1917, right? So 10 over 3 minus pi roughly equals something like that, right? So I'm making this deliberately because I want to show you, just because we have such a small difference between the two numbers doesn't mean they cannot be plotted. So this one will just make it there and we'll say that's pi. You see? So but on the number line, it's not so far from 3 and it's not exactly on 3, but it's also not exactly the same as another fraction that has a recurring decimal. That one. So that's just another way of identifying these. So you can still have those irrational, they're still real numbers, but you can still have the same irrational numbers there. That one. So you can skip this part and then we can just read the part on irrational numbers. No, take your time.
Irrational numbers are real numbers that are not rational.
Okay.
They cannot be written as a ratio of two integers. In other words, you cannot write an irrational number as a common fraction, like
rational numbers.
Irrational numbers can also be shown on a number line.
So you see, we just did that now with pi and we compared it to another rational number. Yeah, carry on.
Here are some famous irrational numbers used in mathematics. Pi is the irrational number that you get if you divide the circumference of any circle by its diameter.
Okay.
Then the number below shows the first 50 decimal places in the value of pi.
Okay, so
yeah,
that's just it. Yeah. So anyway, you can skip that part. I think we should do some exercises. until our child time. Yeah? Maybe that will help you better understand the theory of numbers. Okay, so exercise 1.1. Just read for us what it says there.
Decide whether the following numbers are rational or irrational numbers.
So rational versus irrational. And now I'm gonna need you to be very active in this exercise, right? I don't care if you get the answer right or wrong. If it's correct, we celebrate it. If it's incorrect, we correct it, right? All right, so the first number is?
Square root of 25.
Okay, square root of 25. Do you think it's rational or irrational? You're not sure.
Rational.
Rational.
Yes.
What makes you think it's rational? That's an interesting question. Answer.
No, it's actually
No. Back up your
Rational.
answer. I want to hear you back up your answer.
Nah.
You think it's irrational?
Yeah.
Why do you think it's irrational after you thought that it was rational before?
Cause the square root of 25 is 5, so
Okay. So square root of 25 equals 5. Okay, that's a good answer. That's very correct, by the way. So is the number 5 rational or irrational?
Number 5.
The number 5, is it irrational or is it rational?
Rational.
It's rational.
Yes.
Okay, so you had the correct answer before. Now when I ask you to back it up, you doubt it, and then you say it's the opposite answer. And then when we work it out, you get the correct answer, and now you get to the final answer, which is what I wanted you to back up with. So let's work on that, ne? Let's work on that. You can do without the self-doubt. You can do without the self-doubt. And that's why I say I don't care if you get it correct or incorrect. I just want to hear your thoughts. And if it's correct, we celebrate it. Right? If not, we correct it. That's the simple rule. So let's try again. The number 5 is rational, meaning the square root of 25 is rational. Right? So how would you back up your answer if we started here and the question was, is the square root of 25 rational or irrational? Remember, you calculated it, you got the final answer, and then you said the answer is rational. So I want you to reason like that. Can you do that for us? Eh?
I don't know.
You don't know? Give it a try. Give it a try. How about that? Eh?
But I don't know, like, how to explain it though.
It's okay. We're working on you figuring out how to explain that. Because even if you're not asked to explain it verbally, you would get asked to explain it in written form. So you still need to be able to put your thoughts, nicely. Ne? So again, let's start. Is the square root of 25 rational or is it irrational? And you start in your head, do the mental math if you can do it, and then you put it down. Ne? Just explain to me how it comes in your mind. Then we can correct that. Don't be shy. Or should we do the next one, negative 65.2?
It's rational because it does not have a minus.
Which one?
The
The square root of 25?
Yeah.
That's not the best reason. That's not the best reason because remember what our tree says. Yeah? Our tree suggests we were looking at surds again. Okay. We were looking at surds, but the one that we worked out ended up giving us an integer, or rather a positive integer, right? And what does it tell us? Oh, you went with surd, and then you said it is. Interesting. It's fine. So in this case, the best approach is work it out, find out what the answer is. Then you'll tell us if it's rational or irrational, right? So in this case, this number is rational because when we work out the square root of 25, we get 5. And 5 is a rational number. Okay, so square root of 25 equals 5, which is rational. Okay, then the next number would be negative 65.2. What do you think about that? Is it rational or is it irrational? You can also refer to what rational number means, ne? Where is it? There. Rational means it can be either an integer or it can be a fraction that's terminating or a fraction that has recurring decimals. That's what rational means. Okay, so negative 65.2.
It's rational.
It's rational. Okay, so it's rational. And why do you think that is?
Because
explain. Because why?
because it has an integer.
What about the decimal? It's a fraction because it's got a decimal, I guess. Now, is that decimal recurring or non-recurring and non-terminating, or is it terminating?
It's terminating.
Excellent. So it's rational because it has a terminating fraction. So you are correct. Well done. All right. And then the third one, negative square root of 81. Okay. What do you think? Let's first do the math. What's the answer there?
81.
For negative square root of 81.
Negative.
Yeah, this number here. If we were to solve it, what's the answer? If we were to calculate it.
Isn't it minus 4?
No, not 4. Definitely not negative 4. Should we check with the calculator? Okay. Okay. So what's the answer there?
9.
Remember, we've got negative.
-9.
So it's going to be -9. Is that rational or irrational?
Rational.
Rational. Why?
Because I don't really know like how to explain it. It just keeps. I don't know.
It escapes you. Okay. So it's rational because -9 is an integer, and there's no way we cannot have an integer and it not be rational. Right? So it's rational because -9 is an integer. All right. So the next number is 22/7. Now 22/7 does not exactly equal pi, but it is an approximation, right? But anyway, I'll just put it that away. I'll just put that away. So yes, 22/7. Would you say it's rational or irrational? Okay, this one I think we can also check with a calculator. Right, so if I do 22 divided by 7, 3.1428. Okay, looking at that, what is that an example of?
Irrational.
Irrational.
Yeah.
Okay, that's a good answer. Why?
Because I see that more it starts at 2 2 comma and then it
Okay, so how do we describe
goes
that?
on. Non-terminating,
And
non-recurring decimal.
yes, so that's how you explain it. So a number like 22 divided by 7, which is an approximation of pi, is irrational because it has non-terminating, non-recurring decimals. You get it? You get it? If you don't get it, forget about it. So again, and that's why I'm emphasizing, we do the exercise, we keep referring. It's open book here. You're not in a test. It's open book. We can go back to the page where we learn the theory. Where we learn the theory is in this diagram. So irrational, non-terminating, and non-recurring decimals. All right. So 22 divided by 7 is a good example of that. That one. This one, decimals, yes, but are they terminating?
No. I mean, yes. So
Yes, they are terminating. Are they recurring? Well, since they're terminating, they're not recurring. So then best way would be rational. Yeah. So that's the best way. All right. 3.14. Since that would mean they terminate, we can say that's rational. Okay, you know what? I'll give you homework for this. Go ask your teacher. Yeah, go ask your teacher, find out their thoughts. But I would say, since they terminated it there, it's rational. But I'm happy to hear from anyone else who thinks otherwise and why they think that. And I'll be open to being corrected. You know? Anyway, let's look at pi. So pi is 3.141 something something something. Again,
Irrational.
irrational, 100%. And why is that?
Because it is non-terminating and non-recurring.
Non-recurring decimals.
Yeah.
100%. You're doing great, man. You're doing great. Now let's look at this one. It's 3 times the square root of 15. Okay, that's interesting. So let's work that out. So 15 times 3. So we get 11.618950 something. Is this rational or irrational?
Irrational.
Irrational. Good. Why?
Because it's non-terminating and non-recurring decimals.
Excellent. So you get the idea now, the difference between rational and irrational. Okay, I'm glad you do. So, but that's the whole point. We start out not knowing something, and then we at least leave having learned something. And that's the whole point of you finally getting the gist of what it means to have rational numbers and irrational numbers. And I'm glad that you've gotten here. So well done. All right, so let's do the next example. Given the list of numbers, Okay, so we've got a list of numbers, ne? The numbers, call them out for us. It's these ones here, ne?
Yeah.
It's -7, okay.
Comma 7.
Oh, okay, -7.7, all right. 5, okay.
Square minus 6.
Square root of -6.
Yeah.
Okay, that's interesting. Okay.
8.
The number 8.
Yeah.
Okay,
8.
great.
Square root of 35.
35, okay. What else?
36.
36, okay. What else?
71 over 3.
3. I have to take this call. Ponsolo? Okay, just give me a moment, ne? 10 seconds. Can we end class now? Yeah, I have to take this call. Let's meet next week Tuesday.